Hello, good morning, good afternoon, good evening from wherever you are joining us from. Today is the 4 of Qiskit 4 Phase Ghana version. And once again, it's great to have all of you join us for today's session. I am already excited because we are getting closer to this workshop and it's been wonderful since day one. So we are kindly asking to show a thumbs up in the chat room if you are still with us and you've been enjoying this workshop so far. Let's see a thumbs up in the chat room. Great. Wonderful. Great to see all of you again. Benedict, Esther, Vendan, Sharim, Krishnan. Wow. Great to have all of you back today to this wonderful session as well. Today is day 4, like I already said. We welcome you once again to Qiskit for Faith Ghana version. Okay, so today we spent some few minutes in the breakout room as well. So in the breakout room, maybe we can discuss since day one what we've learned so far. So kindly let's go to the breakout room. Let's share our thoughts, the knowledge we've learned so far for Qiskit for First Ghana version. So we'll join breakout room soon. All right, so let's go. All right, so you're all welcome back from the breakout room. If you had a wonderful session, kindly express that in the chat room. So let's see how you are feeling in the chat room. Okay, so you can see people are quantized, they are very excited, they've moved from ground state level to greater energy state level, and that's great to know. I mean, yeah, excited for today's session. That's great. I mean, there's going to be a lot of entanglement today. I mean, we are already in the superposition state, so I guess we're ready to get entangled. So I will not take much of the time. We are excited for another day as well as we get into quantum computing, getting to learn the basics for which we'll build upon. We are very fortunate to have a very wonderful presenter today as well. In Ghana, he's called the quantum guy, the Ghana quantum guy. And I mean, I won't say much because he will share a little bit of his journey with us and takes us through today's presentation on dynamic circuits. So let's welcome Mr. Emmanuel Ofosu to take us through today's presentation. Mr. Ofosu.
Hi everyone. Okay, so I'll go ahead and share my screen. All right. I believe you can all see my screen. Madam, please, is it okay?
Yeah, yes, please. Very visible.
Okay. So good morning, good afternoon, good evening, everyone. from wherever you are joining us from today. I'm in the person of Emmanuel. I'm a teaching and research assistant at the Department of Physics at the Kwame Nkrumah University of Science and Technology in Kumasi, Ghana. I'll be talking about dynamic circuits in Qiskit today, and a little bit of my background. I'm a recent qubit by qubit alumni. I've also done Humanium and then the Qiskit Global Summer School this year. I'm on all social media platforms. I am Fusi Emmanuel. You can see my personal website there, and of course, they call me the Ghana Quantum Guy. So I'll take you briefly on my quantum journey. So last year, I got a full funding from the coding school to attend the qubit by qubit, which the program started on 17th September 2022. Before this program, I had little, like no knowledge about quantum computing. I didn't even know what a qubit was, in fact. But then, after going through the session, and then earlier this year, January, I participated in MIT's IQ Hack, where I worked on the IonQ Quantum Machine Learning Challenge. And then I went on to help organize my country's first in-person quantum computing workshop. And then, of course, I have attended the summer schools and then this current one. I have so far won more than $3,000 in quantum computing scholarships, and I have about 15 quantum certificates. So yes, I'm quite young in the journey. It's 1 year and some months, but then I'm making progress. And I hope you enjoy my lecture today. So the lecture today is going to be about dynamic circuit in Qiskit, like I said. I'll firstly talk about classical feed-forward and control flow. Then I'll go ahead and talk about the 4 control flow constructs. And then I'll introduce the Toffoli Gate, the phase gate, and then the concept of repeat until success. Now, let's go. All right. So when we talk about classical feed-forward and control flow, those of us new to programming and those of us who want to refreshen up, when we talk about feed forwarding, feed up, feedback, what it basically means is that feed forward is I am at a specific point in time, and then I want to know where I am to go next. If you want to know where you want to go next, that is the future occurrence. We call that a feed forwarding. But if you want to analyze how you are going, you want to reflect on how you are going, that is what we normally call the feedback. So classical feed forwarding basically means that we are planning where to go next in future. But then I will explain it more in the quantum context. And then when you talk about the control flow, what it means is that I have a specific condition. So let's say the condition is it raining today? And then if it is indeed raining today, then we perform a certain action. Else we will perform a different action. So when we have things like that, it means that we are trying to control the flow. Now, let's bring it in the quantum context. So classical feedforward refers to the ability of us to measure qubits in the middle of our circuit and then perform an additional quantum operation that depends on the measurement outcome of the qubits that we have already measured. So these features are sometimes referred to collectively as dynamic circuit. So if you look at the diagram on the right, we have an unknown state. We don't know the state of this particular qubit, but then over here we perform some measurement. And you know from the previous lectures throughout the week, we've iterated on the fact that anytime you perform a quantum measurement, it brings you into the classical world. So you are either going to result in the 0 state, the 1 state. So measurement is the thing that breaks the superposition. So if you are superposition, you are in superposition, let's say the plus state, you are between the 0 state and the 1 state. Measurement will bring you to either the 0 state or the 1 state, like a definite point, not a superposition. So we are saying that, okay, we have an unknown state, we perform some measurement, and then if the results of the measurement in this case is 1, we will apply an S gate. But then if it is 0 in this case, we don't do anything. So basically that is what we call classical feed forward. Now, in Qiskit supports 4 control flow constructs for classical feed forwarding. So we have the if statement, the switch statement, the for loop, the while loop, and then I will be taking them one after the other so that at least by the end of this lecture we will have a pretty good explanation of what classical feed forwarding and dynamic circuits in Qiskit means, and that will help us to also tackle the lab for today. Now let's jump right into the if statement. So the if statement is declared this way. So we have quantum circuit. Quantum circuit can mean whatever naming convention that you have given to your quantum circuit. So normally it's QC is equal to quantum circuit, and then we specify the number of qubits and then a classical bit. So the method is quantum circuit dot if underscore test. Now the if statement is used to conditionally perform operations based on the value of the classical bit. One thing that you don't have to forget and you have to always remember is that whenever we perform measurements in quantum computing, the outcome, the results, we store it in a classical bit. Now what we are doing in dynamic circuit is after we have made our measurement and then we have a value on the classical bit or in the classical bit register, what we are doing is we take that value and then perform some control flow on it. And in this case, I'm introducing you to the if statement. So what the if statement does is to perform operation based on the value of the classical bit that we have obtained now. Now, I like to always lecture with more examples because we look at it from different dimensions and then we understand it better. So I'm going to introduce you to an example below. And in that example, we first apply a Hadamard gate to a specific qubit, and then we make our measurements. Now we are saying that if the results of the measurement is 1, we will apply an S gate on the qubit. And then it has an effect. So we know that from the lecture yesterday, we know the function of the S gate. It flips the qubit, you understand? So the effect of the S gate that we are applying, if the result is 1, is to do what? Flip it back to 0 state. And then we will make a measurement of our qubit again. And because the condition is that if it is 1, we should flip it to 0, the resulting measurement outcome is going to be 0 with 100% probability. Now, this is how the circuit looks like in code. So we do our normal imports from Qiskit circuits. We import our quantum circuit, the quantum register, and the classical register. Now, for the classical register, we just provide one classical register and then we label it as qubits or we name it as qubits. And then for the quantum register too, we have for the quantum register, we name it as qubits, and for the classical register, we name it as CL bits or classical bits. Now, what we are doing is the fifth line is we are doing the normal thing that we have been introduced to throughout the week. We are constructing our circuit. So the quantum circuit, then we pass in the qubits and then the classical bits, and then we are saving it as qubits. And then we move on to specify where the naming convention of our qubit and classical bits are supposed to start from. So over here, we are saying that our qubit is Q0 because it's 1, 1, and then the control bit is C0. Now, from the preamble, we are supposed to apply a Hadamard gate on the first qubit. Remember that in programming, we always start counting from 0, very important. So Q0, anywhere you see Q0 throughout this lecture, it means that the Q0 is the first qubit, Q1 is the second, and in that order. So we are applying the Hadamard gate, the H gate, on the first qubit, and then we perform our measurement. Now the measurement works in such a way that we are um, we are measuring the first qubit and storing the value in the first classical bit over here. Now here, this is where the dynamic circuit comes in. The syntax for the if test or the if test statement in the dynamic circuit is we first bring a wait and then we say circuit dot if underscore test. Circuit over here can be replaced with whatever naming convention you used for your quantum circuit. And then the if test takes two parameters. Where are we measuring our classical bit from? And then what value are we checking? So we are saying that measure the classical bit at the first classical bit, the C0. And then we are saying that if the value is 1, what do? We apply an S gate to the first qubit. After that, we move out from the if statement and then we measure the circuit again on the first qubit and then the second qubit. Then we use Matplotlib to draw our circuit. Now, this is how our circuit will look like when you output that particular data. So you can see that we are applying a Hadamard gate on our first qubit. We are taking some measurements and storing the measurements on the first classical bit. Over here, we have only one classical bit. We are storing the value on the first classical bit. And then this is where our if statement comes in. Whenever you see this dot in dynamic circuit, it means that we are checking for the condition if it's 1. You see a black dot. The black dot signifies that we are checking the condition if it is 1. And then we are saying that if it is 1, what do? We apply an S gate. And then after that, we take measurement of the qubit again and then store it in the classical bit. So basically, this is the first example of the if statement in our dynamic circuit. I want you to give me thumbs up in the chat if you understand what I've said so far. If I'm going too fast, then kindly prompt me so that I can slow down. And then if you have any question, put it in the chat and then you'll be attended to. Thank you. All right, I can see thumbs up. Okay, somebody says, I should explain the diagram again. The black dots. Okay, so let me take it one more time. So our preamble is to first apply a Hadamard gate to our first qubit. If you see Q0, that is the first qubit. We are applying a Hadamard gate on the first qubit. And then we measure the condition or the state of the qubit and store the value in the classical bit. I was going to say first classical bit, but because we have only one classical bit, it's the same thing. So we apply the Hadamard gate, take measurements, and then the if statement over here, that is where the focus is, because we know how to do measurement and apply H gate and all that. We know how to do it. The addition we are making today based on the dynamic circuit is the flow control and then the classical feedback. And I'm saying that if you go back and check the code, the condition was that if we measure the classical bit, and then the value that we get is 1, that one is represented by this black dot. When we go on, then we test for the condition of the thing being 0. You understand the difference between this dot and then the one I'll show you. But basically, if it is 1, the dot is black. But if it is 0, the dot is white. Basically, that is the difference. And then what we are doing is we are saying that if it is a 1, we apply an if statement. And that means that we are introducing an if statement, and then we are applying an S gate over there to flip it back to 0. And then after that, if you want to know what is going on in our circuit, you have to perform measurement. So we perform measurement and send it back to the same classical bit. I believe we should be all done by now. So the way statement can be given as an assignment target, and then the purpose of the else block that we introduce, if you check correctly, we introduce an else block somewhere. The else block is to make sure that whenever the previous code did not run, then we can have another iteration. So like you have an if. So if it is going to rain, go with an umbrella, else go without an umbrella. So you realize that we need that. So in this second example, we are doing the same thing, but then we are adding a little bit of complexity. So we will initialize our registers with 2 qubits and 2 classical bits. Then we will apply a Hadamard gate to the first qubit, and then we perform measurement on the first qubit. Now we are saying that if the result of our measurement is 1, then we are going to apply a Hadamard gate on the second qubit. Otherwise, we will apply an S gate on the second qubit. And finally, we'll measure the second qubit as well. If you don't get it here, I think the code will explain itself. So this is what we are doing in the code. We are initializing 2 quantum registers and storing their name as qubits. And then we do same for 2 classical registers. They are called CL bits. And then we construct our quantum circuit with these qubits and classical bits. The qubits and classical bits, we are naming them. We are saying, because they are 2, we are always starting from 0. So Q0 and Q1 for the qubits, C0 and C1 for the classical bits. Now we go on to apply a Hadamard gate on the first quantum bit or qubit. Now what do we do again? We perform measurements on the first quantum bit, and then we store the outcome of our measurement in the first classical bit. Now we come to the if statement. The if statement, we are saying that, okay, so now we have value at our classical bit, the first one. We are saying that if it is 1, we are applying a Hadamard gate on the second qubit. Q1 is the second qubit. Else, we are applying an S gate on the second qubit. After everything, we will perform measurement on the second qubit, and then store the value in the second classical bit. After that, we will plot it in matplotlib and then draw our circuit. So this is how it looks like. We have our Hadamard gate on the first qubit. We apply or we do some measurements and store the value in our first classical bit. Now I said if you see this black dot, it means that we are checking for the condition if it is 1. If it is 1, we are applying the Hadamard gate on the second qubit. Else, we are applying an S gate on the second qubit. Now after that, what do? We perform measurement on the second qubit and store the value in the second classical bit. I think we should get it now. At this point, I'll pause for questions, and then if you don't have any questions, we can move on. But if you get me, please kindly give me thumbs up in the chat so that we can move on. Okay, I think we are good to go. So we move on. Now, add more examples, a third one. By a third one, we are checking for the condition if there is some zero involved. So what we are doing is we are going to apply a Hadamard gate to 2 qubits like we have done, and then measure them. And then we are saying that if the result is 0, 1, that is the first qubit is 1. You know, Dr. Nibe talked about the little endian, the little endian in so the little endian, and then what we are going to do is, excuse me please, I'm coming. Okay, so the little endian basically means that instead of normally counting from the left, we are going to count from the right instead and go left. So what we are doing is we are saying that we are checking for the condition if the first qubit is 1 and then the second qubit is 0. If that condition is met, we will apply an S gate to the third qubit. Finally, we measure the third qubit, and then note that for clarity's sake, we will introduce a third state for the classical bit as well, and the state is going to be 0 in the if condition. And then overall in the circuit drawing, the condition is indicated by circles on the classical bit being conditioned on. And this is what I've been iterating on. I'm saying that a black circle indicates that the condition is 1, while a white circle indicates that the condition is 0. And this is how the code looks like. So I've explained it time and time again. The first one, after doing our importation, we are initializing 3 quantum registers, storing them as qubits, 3 classical registers, and storing them as CL bits. Now we finally construct our circuit names, C1, C2 for the classical gates. Then we will measure Q0, which is the bit. We will go on to measure the second qubit and store the value in the second. It's in the form of 1, 0, 0. Remember that the little endian, so I'm reading from the right, which is 1, 0, 0, not 0, 0, 1, like you can see over here. We are checking for the condition if the first on the first, if we read 1 on the first classical bit and we read 0, 0 on the rest of the classical bits, which is the second and then the third, that is the only place that we perform the flipping. That is when we flip the third qubit. I don't know if you get me. So because here is a black dot, we are saying it's supposed to be 1, 0, 0. The person who asked, are you okay? So we are checking for the condition if here is 1 and then here is 0 and then here is 0. I don't know if you get me now. Okay, he said it's okay. If there are no more questions, yeah. If there are no more questions.
Another one there. There's another one there. Can you design similar circuit using IBM Composer?
Of course, you can design similar circuits using IBM Composer. But for now, what I've not checked is whether you can perform this dynamic, this particular dynamic part of the circuit in the IBM Composer. But I know it's capable of doing that. I've not found out yet. But in code or in the IBM Quantum Lab, of course, you can do this. That's where I did this. So yeah. All right, I'll go ahead. Now we are moving on to the switch statement. The switch ring dot parameters. So the switch statement is the switch statement allows us to specify more cases. So if the condition is if it did not rain, send umbrella, or if it rained, send umbrella or go out with an umbrella. Else, if it is shiny, also go out with an umbrella. That is the first if statement. But then what if we are having two or more conditions? What do? So it's raining, it's shining, even though okay, that's happening sometimes. Shining at the same time. So I have two conditions. And then for both of them, I need to do what? Go out with an umbrella. That is where you use the switch statement. So in Python, you can do if else. You can do if. But then for the proper way of doing it is to use a switch statement instead. So we have more cases. Now I'm introducing you to a different example under the switch statement because we learn more or best with examples. What we are going to do is we are first going to apply Hadamard gate to a qubit. So we will always start from the easiest to do, and then we will measure it. Now we are saying that if the result of our measurement is 0, we are going to apply an S gate. But then I want to ask a question, and I want you all to respond in the chat. If I measure and my result is 0, and then I apply an S gate, what will be the state of my qubit now? I want to see answers in the chat. If my result is 0 and then I apply an S gate, what will be the state of my qubit now? All right, most of us are getting it. So the state of our qubit will be a 1, right? So that is the first condition. Now the second one is if we measure and the result is 1, we are applying a Z gate. What will the Z gate do to the 1 state? I want answers in the chat. Quick. Somebody said flip, but where will it flip it to? Where exactly will it flip it to? Okay, so if my result is 1 and I apply the Z gate is a rotation on the Z axis. So I'll still have a 1 with 100% probability, but then something will happen to the phase. So the Z gate, if you apply it to 1, it will still be 1, but then something will happen to the phase. That is why if the result is 1 and I apply a Z gate, I'll still get a 1 with 100% probability. But then if you check the phase, you do it mathematically, something would have happened. Okay, so we can move on. So this is how it looks like in code. We are always doing the normal things. I won't explain this part again, the top part. So we have 1 qubit and 1 classical bit. We are applying an 8 gate on the qubits that we have and then performing measurement on the qubit and storing it in the classical bit. Now this is how we use the switch statements, the syntax. We have the name of our circuit here, and then what we will do is switch, and then because over here we have only 1 classical bit, we will use the C0, and then we are bringing the case so that we can introduce the cases. Now what we are saying is if the case is 0, if after reading the state of our qubits is the state of our classical bit, is 0, we are applying an S gate on our qubit. But then if you read and the state of our classical bit is 1, we are applying qubit, or the only qubit that we have. After that, we will take measurements of our qubits and then our classical bit, and then we will draw it again. So this is how the output looks like. We have our Hadamard gate over here. We are performing measurements on the first qubit and storing it in the first classical bit, or the only classical bit that we have. Now, if you see dots here, what does it signify? I want to see. If you see dots here, what does it mean? If you see a black dot, what does it mean? Okay, so we are checking for the condition of our classical bit being 1. We are saying that if it is 1, what are we doing? We are performing a case and flipping it to X. And then if it is 1, we are performing, if it is 1, we are performing a Z on it. But if it is 0, we are performing an X on it. And then after that, we will take our measurement again. I'll pause for questions If there are no questions, I will move on. Any questions up to this point, please? Any question up to this point? If you understand what I've said so far, kindly give me thumbs up in the chat. It makes the lectures more interactive. All right, I'll move on. So there is one question. Okay, there is more.
There is one question.
Okay.
I say that are we must to apply X and Z with order? He's talking about order when we are applying the gate.
So this is just how we wanted things to play out. So you can, if the condition is 0, we could have performed a Z instead, and then if the condition is 1, we could have performed an X instead, or perform a Hadamard on it, or perform control not, or whatever that we wanted to do. But over here, this is how my example played out. So it's not stringent. It's not stringent, and that is always going to be the case. All right. Is there an additional question?
Yeah, he went on to say that, but with the switch run, then he included the same thing because we are having a black dot. The same person, with the switch run, then he came down and he said, because we are having the black dot. So it's, yeah.
Okay. So I don't get it. I don't get the question clearly.
Okay, so he's the one who asked. The first person asked, are we must to apply
I
X
think I
and Z
get
with
it now.
order?
I think I get it now. So
I think you
the
can
question
also
is,
ask the question.
Okay,
okay,
so if
but
the person, yeah, you can.
I think I get the question now. He's asking, why is there a 0 and then a 1 case over here, but then the dot is still black? Is that what the person meant? Yes. Okay.
Yeah.
So if you go, let's go back to our code. Let's go back. So if you come here, you realize that, of course, we were supposed to have a black and then a white dot. You understand? But so far, if you read the documentation on dynamic circuit, IBM is saying that they are still developing the dynamic circuit. So one thing that going through or preparing this lecture, I realized is that because Qiskit is more open source, you can contribute as an individual. You can contribute. So we've realized one bug in the code, right? We've realized that if for the switch statement, if the condition is 0, they are still representing it with a black dot. So we can contribute to that. So just jot it down. If you want to be a Qiskit advocate, you can just contribute that to the Qiskit open source, and then you can become a Qiskit advocate with that. So yeah, if you discover the bug, I think you're supposed to the black dot is supposed to be for the 1 case, and then the 0 is supposed to be for a white dot. So yeah, thank you. Any additional question? All right.
I
So
think
I'll
we have
move
to.
on. Okay. So because the example uses a single classical bit, the example that I showed you uses a single classical bit. There were only 2 possible cases, right? And then that is the results using the if statement. But the switch case is mainly used for when branching out. We are branching out of the classical register composed of multiple classical bits. So we are going to, I'm going to show you another example, and then we look at how it will play out. So this is the how it play out. So we have an if statement, and we are saying if this happens, do this. If this happens, do this. Else, if this happens, do this. But then you realize that there will be the need for a default case. Like if nothing happened at all, what should we do? The default case. And the default case is going to play out if none of our preceding cases in the switch statements are what executed. And then you should know that in a switch statement, only one of the blocks will ever be executed. Only one, because we are testing for different conditions. There will never be a fall through. Just one case will be executed time and time again. So let's take another example. In this example, we are going to apply a Hadamard gate to 2 qubits, and then of course we are performing some measurements, and then we are seeing that if the results it's either 0 0 or 1 1. What does 0 0 or 1 1 mean? In the chart, what does it mean? Which one is the first qubit and which one is the second qubit? So we are saying that, if the result is either 0 0 or 1 1. But what does the 0 0 or 1 1 mean? Which one is the first qubit and which one is the second qubit? Remember the little endian naming convention in Qiskit. So this one means that it's either this is the first and this is the second. And this one means this is the first and this is the second. So we are saying that if the result is 0 0 or 1 1, the first qubit and then the second qubit both turn out to be 1 or both turn out to be 2, we are going to do what? Apply a Z gate to the third qubit. And then if the result is 0 1, which basically means that the first qubit is 1 and then the second qubit is 0, we are going to apply a Y gate. And then if none of the preceding cases matched, which means that if the result is not 0 0 or 1 1, and then it is not 0 1, we are going to apply an S gate. That is the default case. And then finally, we are going to measure the third qubit. So this is how it plays out. I've explained this part several times, so I'm not going to do that again. So you can see that we have 3 qubits and then 3 classical bits over here. We are applying a Hadamard gate on the first qubit and then the second qubit. Now we are going to measure the first qubit and store the value in the first classical bit. We are going to measure the second qubit and store the value in the second classical bit. Now we introduce our switch statement on the control bit or the classical bit. Sorry, classical bit, not control bit. And then we are saying that if the bit value for our classical bit that we have measured is 0 0 0 or 0 1 1. You realize that we've not spoken about this and then this. So in the condition, it was either 0 0 or 1 1. It's for clarity's sake. If it is 0 0 or 1 1, what we are going to do is we are going to apply a Z gate on the Q2 is what? The first qubit, the second qubit, or the third qubit? Q2 is what? I want you to respond in the chat. Q2 is what? The first qubit or the second qubit or the third qubit? The third. So Q2 is the third qubit. What we are doing is we are applying a Z gate on then what? The third qubit. Now we test for the condition if it is 0 1. Remember, our focus is on the last two, which according to little endian is the first two. This 0 1. So we are testing if it is 0 1, then we apply a Y gate on the third qubit. If none of this is true, what we are going to do is what? We will resort back to our default, and the default is to apply an S gate on the third qubit. Now, when all these conditions are met, or either just one of them is met, what we are going to do after us is to measure our third qubit and store the value in the third classical bit. And then we go on to use Matplotlib to draw and visualize our circuits. So this is how our circuit will look like. Again, we realize that we have conditions of 0 and 1 which were not properly illustrated by Qiskit, and I said this might be a bug. So if somebody will hop on it, that would be nice. So the first qubit, the second qubit, we are applying Hadamard gates and then performing measurements to read their outcome. Now we are saying that if the we have the condition of I'm coming. So if you have the condition of 1 1 or 0 0, what we do is apply a Z gate. So this gate is for 1 1 or 0 0. We apply a Z gate. And then if the condition is 0 1, we apply a Y gate. If the condition is 0 1 over here, we apply a Y gate. And then if the condition is default, if here is the default, we do what? We apply the S gate. And then when we are done with everything, we apply what? Measurement over here. Any questions? So far, any questions? All right, I'm making sense. Let's move on. So we've treated the switch gates and then what? The if statement. So let's move on.
There's a question.
There's a question. Okay.
There's a question.
Okay, can I go back to the code screen?
Can you go back to the code screen?
Okay. Is there a question over here? Do you have a question? If you have a question, unmute and ask me, please. All good. Okay. Then we move on. So now the popular for loop. This is our for loop. So the for loop, this is how we start with it. We have the name of our quantum circuit, and then we do for underscore loop. Don't forget the underscore. It's always underscore. And then the for loop is used to iterate over a sequence of classical values. So the thing is, we perform measurements on our qubits and store it in a classical bit, and then we get a sequence of classical values. We will iterate over them. Iterate means, let's say we are counting from 1, we will go from 1 2 3. We have a specific number of iterations, so we are going to do the iterations for a specific time. Specific number of times. That is where we use the for loop. I'm using the word specific because very soon I'll talk about the while loop. The difference between the while loop and then the for loop is that the for loop has a specific number of iterations. The while loop can go on and on and on and on. And then when we iterate over the sequence of classical values, we then perform some operations during each iteration. So let's say we go for the first iteration, then we perform an action. We go for the second iteration, we perform an action in that order. So like I said, examples are the best way to learn. So we are going to introduce the for loop, and then we use the for loop to apply 5 S gates. So you know the number 5 is specific. So we are applying the S gate 5 times to a qubit, and then we measure it. And because we are going to perform an odd number of S gates, the overall effect is to flip the qubits from 0 state to the 1 state. Now I have a question. If I have a 0 state and I apply an S gate on it 5 times, so I have 0, I apply an X, then I apply an S again, then I apply an S again. So let's say X to the power 5. What will be the resultant state? I know it's already in the slide. So if I have a 0 and I apply an S gate 5 times on the same 0 state, what will be the resultant? A 1, correct. But what if I have a 1 and I apply an S gate 4 times on it? What will be the resultant? If I have a 1 state and I apply an S gate 4 times on it, what will be the resultant? All right. So for those of us who are not getting it, if I have a 1 and I apply an S gate, it will become 0, and I apply an S gate again. So this is my first S gate. If I have a 1, I apply my first S gate, it becomes 0. And I apply my second S gate, it becomes 1. I applied my third S gate, it becomes 0. And I apply my fourth it becomes what? 1. So this is how come we are getting 1. All right, you get it. So the last statement says that because we have an odd number of S gates, the overall effect is to flip the qubit from the 0 state to the 1 state. So if I have a 1 and I want to still get a 1, I should apply the S gates in what order, whether even or odd. It's supposed to be even, right? But if anytime you apply the X gate for an odd number of times, you are always going to get the opposite of the state you started with. So this is how the for loop is implemented. So we have our only one quantum register, we have only one classical register, and then we are constructing our quantum circuits. The naming convention is Q0 and then C0. Now this is how the syntax for the for loop looks like with circuit.for underscore loop. We are using the range, so we are providing a range. You understand? And then the range over here is 5. And then we are saying that if for every iteration that we will go, we are applying the S gate on what? The first qubit. When we have iterated for 5 times, we are going to do what? We are going to apply measurements on the first qubit and store the value in the first classical bit. And then we draw our circuit. So this is how it looks like. So it doesn't really matter if you see Q5 here, it doesn't mean it's the fifth qubit. No, this part you can change it. You can change it wherever you want to, but then it's supposed to be the first qubit and then the first classical bit. So we are saying that we are doing the iterations, and remember, programming always starts counting from 0. So we are doing the iteration for how many times? 5 times, and then we are applying an S gate in each iteration. When we are done, we perform measurements on the qubit and store the value in our classical bit. Now I'll move on to talk about the while loop. So I said the while loop and then the for loop, they have something in common. They are all iterating, but then the while loop is used to repeat instructions while some condition is satisfied. So as long as the condition is satisfied, we are going to keep repeating the instructions. We are repeating the instructions on like as long as that condition is satisfied. So I'm introducing another example again. In this example, we are applying the Hadamard gate with 2 qubits or to 2 qubits. We will measure them. All right. Now we are saying that we will create the while loop that repeats this procedure while the measurement outcome is 1, 1. So we are saying that as long as we measure and our outcome is 1, 1, we are going to keep applying the Hadamard gate. And then as a result, the final measurement should never be 1, 1, with the remaining possibilities appearing with approximately equal frequency. Okay, so this is how we do it in code. You understand the first part. And then this is us applying the Hadamard gates on the first qubit and then the second qubit. We are performing measurement on them individually. And then this is our while loop. We are saying that if we read the classical bits and the states of the two of them is 1, 1. The first is 1 and then the second is 1. We are applying what? The Hadamard gates on the first qubit and then the second qubit. And then we will measure the first qubit and then into the first classical bit. Then we measure the second qubit into the second classical bit. So this is how it also looks like. Applying Hadamard gates on the first and second, measuring them, and then applying the while loop in as much as or until they ceases to become 1, 1, we will continue applying the Hadamard gate. So you see black here, this one is correct. It means 1, 1, and then we are applying as long as they are 1, 1, the classical bits are 1 for the first classical bit and then 1 for the second classical bit. We are the Hadamard gates on the first qubit and then the second qubit, and then I am performing measurement on them and storing them at the first classical bit and then the second classical bit, respectively. Now, for the next section, we are going to talk about the repeat until success part. So we are almost done with the lecture. We are going to talk about the repeat until success part. But then, throughout the week, you have been introduced to the H gate, the S gate, X gate, the CS gate. What else? And then the poly gates, right? The X, the Y, and then the Z. But then to be able to handle repeat until success, I need to introduce you to two more additional gates. The first one is the Toffoli gate. And then, so we will look at the Toffoli gate, and then the second one will be the phase gate before we apply that principle to the repeat until success, and that will be the end of the lecture for today. So let's look at the Toffoli gate. The Toffoli gate is almost like the control knot gate. The control knot, the idea of the control knot is we have a target and then a control. So the target and our control. So it's acting as a target. But the Toffoli gate introduced two controls and then one target. So two controls and one target. The Toffoli gate was invented by somebody called Tommaso Toffoli, and it is a universal reversible logic gate, like the classical reversible logic gate. Anytime you want to represent classical reversible logic gates in a quantum wise, you use the Toffoli gate. It is also known as the control knot, CC knot, control knot. So if you anywhere you hear the Toffoli gate, it means the control knot. And the naming convention comes with the definition. So control knot means we have control, and then the target. It has 3 bit inputs because there's supposed to be a first control qubit, a second control qubit, and then a target qubit. So 3 inputs and then the 3 outputs. The condition is if the first 2 bits, the controls, are both 1. Remember, for the control knot gate, if the control, what we are using to control the gate is 0, we will do nothing on the target. If it is 0, we will do nothing on the target. Unless it becomes 1. That is where we will perform an action on the target. So the Toffoli gate acts the same way, just that over here we have 2 controls. So the condition is if the first 2 bits, quantum bits, are 1, they are both 1, then we will invert the third qubit. Otherwise, everything should stay the same. That is the Toffoli gate. So this is how the matrix looks like. If you want to express it mathematically, this is how it looks like. I'll not go into this. I'll move on to how it looks like. So anytime you see the Toffoli gate, this is how it looks like. We have first dot, second dot, and then there is this knot here. So the first is the control, and then we have the target here. You see it represented this way somewhere else, especially if you are not using Matplotlib and then you are using other visualization libraries. This is how the Toffoli gate looks like. And then this is how we use it in Qiskit. There are 2 ways. You can either you import the CCS gate, and then if you want to append the Toffoli gate on your circuit, you bring the name of the circuit, you bring append, and then you introduce the CCS gate over here, and then you specify where your control should be, where your first control should be, your second control should be, and your target. I don't like doing this one. I like the simple one. So, or you just bring the name of your circuit, then you do .ccx, and then you have, let's say, a variable containing where you have specified your first control qubit, your second control qubit. So let's say I do controls is equal to, let's say, Q 0, and Q1. Then I'll just call that over here, and then I'll specify my target in the same manner. I'll specify where my target is supposed to be in the same manner. So basically, that is how the Toffoli gate looks like and how it works. I'll move on to the S gate or the phase gate. And then if there are no questions, yeah, there are no questions. So this is the S gate. The S gate is otherwise known as the phase gate. The phase gate. And it is a gate that performs a rotation on pi on 2. Those of us with very deep mathematics background, if you say pi on 2 in radians, what does it mean? Pi on 2. Pi on 2 in rotations, what does it mean? Pi on 2. Pi on 2. What angle are we? By what angle are we moving? Pi on 2. All right, we are getting it. So normally when we say pi, we are representing 180. So if we divide it by 2 over here, we are performing 90 degrees rotation. So the S gate is what? It performs a 90 degrees. So if you see pi on 2, it basically means that we are performing 90 degrees rotation around the Z axis. Around the Z axis. That is the phase gate. All right. So the phase gate performs a rotation about the Z axis on the Bloch sphere. And then it specifies the amount of rotations in radians, but the movement of the phase gate is counterclockwise. It doesn't in direction. It doesn't move clockwise. It moves counterclockwise, or what we normally call the anti-clockwise. And it's mathematically represented this way. So we have the S or the P is equal to 1, 0, and then 0I. And then if you want to use it in Qiskit, you bring the name of your circuit. If it is QC or circuit, then you do dot S, and then you specify the qubit you want to rotate by 90 degrees. I believe we get it from here. So I brought in some few Bloch sphere visualizations. So in the figure below, the phase gate is applied to a qubit in the plus state. In the plus state. If I have a question, if a qubit is in the 0 state, how can I get it to the plus state? If a qubit is in the 0 state, how can I get it to the plus state? What do I do? What gate should I apply to the qubit in the 0 state to get it to the plus state? All right, we are getting it correct. So if a qubit is in the 0 state, we apply a Hadamard gate on it, and then we bring it to the plus state. You understand? Now, if the qubit is in the plus state, as mentioned here in this condition, and then we apply the phase gate, the resulting gate will be in the positive I imaginary domain. Are you getting, like as visualized here? So it will travel this way and come here. And you can see that the angle it has subtended over here is what? 90 degrees. Any question? Give me thumbs up if you are good. Okay. So now let's use the knowledge you have gathered from the phase gate, the S gate, to work on our repeat until success. What does repeat until success even mean? Sometimes the outcome of our process is random and the results you get isn't what you wanted. So what can we do? If I'm running a specific measurement using the dynamic circuits, in the middle of my circuit iteration, I've performed measurements, and then the outcome of my measurement is random. So if I'm expecting 0, 1, it's not giving me 0, 1, it's giving me 0, 1 sometimes, and then 1, 0 sometimes, 0, 0 sometimes, 1, 1 sometimes. And then the 0, 1 I'm expecting is not periodic. It's not periodic. It means that it's random. The values I'm getting is random. So in that case, what do? You try again, because if you have 100 times of doing something, the probability of you getting it right within that 100 times space is very high than doing it just one. If you do it once, whether you are right, you are right. Whether you are wrong, you are wrong. It's just two. But if you have a sample space of 100, you can do more. So you can try again and try again and try again. That is what we mean by repeat until success. So if I'm finding, or I'm trying to find the 0, 1 state, I will repeat it until I get enough evidence statistically to show that, of course, what I have measured is the 0, 1 state, even though there are these outliers in my value. So as long as there is some non-zero probability, immediately the probability of getting the thing tends to 0, it means there is nothing that you can do again. But as long as the probability is not 0 but it's 1 or non-zero, to get our desired outcome, we can repeat the process until there's a guaranteed results that we wanted. And then thankfully, most of the time, you only go through few repetitions before you get your results. So this is how we are going to do it. So in this section, we will use the repeat until success idea to build a rotation gate. So this is called a rotation gate. From the finite gate set that we have discussed, the Toffoli, the X, the X, and then the Harderman, where the 0 on pi is an irrational number. So specifically what we are going to do is cos theta is equal to 3 on 5. And this construct is adapted from Nelson and Chuang, the quantum computation and quantum information, the 10th anniversary version. And it is exactly exercise 4.41. And it demonstrates the universality of what the finite gate has given above. So this is how we do it. The way construction works is that we begin the circuit that acts on 3 qubits. One of the qubits is the target qubit, and our goal is to perform the rotation on this qubit. The other two are syndrome qubits that we will measure, and then the measurement results from the syndrome qubit will tell us whether our operation was successful or not. If both the syndrome qubits read 0, then we will know the gate was performed successfully. Otherwise, we will reset the qubit and try again. We will need dynamic circuit in order to condition the repetitions of the circuits on the measurement. So our first task, actually this part of the repeat until success is adapted from today's lab. I just decided to go through with you on the first one so that you can do the second one. So our first task in that lab is to create a function that will return that circuit, this particular circuit that we have over here. Our first task is to create a circuit or a function that will return this circuit. And here is the image. So we need to apply Hadamard gates, Hadamard gates, Hadamard gates. So if I have, and then what gate is it? Is this particular gate? What gate is this? I want to see your responses in the chat. Okay. Okay, we are getting it. And then, so we are getting it. This is the Toffoli gate. What about this? What about this gate? What about this one? Okay, I'm seeing phase gate over here, which means we are learning. So you can see over here that we are applying Hadamard gates and then applying the Toffoli gates. Then we will go on to apply the phase gate on the target qubit, and then apply a Toffoli gate on the 3 qubits, with the third qubit being our target. We will go on and apply the Hadamard gates on all of them again, and then after that we will measure the first 2 control bits and store them in their respective classical bits. So this is how the code looks like, but for simplicity's sake, I constructed something called a base circuit. So this is a base circuit where anytime I call it, I'll just use it. So the function of this was to take a circuit as input, and then we will modify that circuit. The base circuit, the function is to take a circuit as input, and then I'll modify it. Whenever we need a fresh circuit, we just do what? We will just copy the base circuit. And this is how the base circuit looks like. I have a quantum register, 2 of them, and I'm calling them control. and then I have additional one quantum register, and I'm calling it what? A target. And this is for the purpose of what? The Toffoli gate. Two controls, one target. And then I will make mid measurement of the classical. So classical register, I have two of them, and then I'm calling them mid measurement. The measurements I'll perform here. And then I have the final classical register. I'm calling it the final, and it's one. So the base is what? The quantum circuits. We have our controls, our targets, the mid measure, and the final measure. So in the next cell that we will look at very soon, we are going to fill the trial function so that they construct the circuit by taking the following steps. This is what it is going to do. Remember the focus of the repeat until success for the first exercise under this very name. We are going to do what? What we are trying to do is to do or construct this circuit that we have here. This circuit that we have here is to construct this circuit that we have here. That is the aim of the repeat until success in that particular lab. So our aim is to do what? You can see we have three Hadamard gates applied to each qubit, the controls as well as the target, and then we apply a Toffoli gate between the control register and then the target qubit, and then yeah, so we can do this by using the CCX or CC knots. And then I've showed you two ways of constructing the Toffoli gate. So whichever approach that you use, that will be good. And then you can see that we have an S gate in the middle. We apply the Toffoli gate again. And then lastly, we applied our Hadamard gate, and then we do our measurement. So this is how it looks like. So this is the quantum circuit, quantum register, the control. And what we are doing is we are applying the edge gates on the target, and then applying the edge gates on the two controls, applying the Toffoli gates with our controls and our targets. We are applying the phase gates on our targets, and then we are doing this again. We are applying the Toffoli gates on our controls and our targets. We apply the edge gates on our control. We apply the edge gate on our target at the same time. After that, we will measure our controls and then measures, and then we will just bring the whole thing to visualization using MPL. This is how it looks like after us. So if you go to that particular lab and then the outcome of your circuit doesn't look like this, you should know that you are not doing something right. Ladies and gentlemen, thank you. At this juncture, I'd like to take more questions. If there are no questions, then thank you. Thank you. Thank you.
Yeah, hello. I have a question about the yes, can I? Yes. So
Go ahead.
I wanted to ask about the Toffoli gate.
Okay.
So you said it's a universal gate. So does it mean that we can find other gates or we can use it to generate other gates? Or what do you mean by universal gate?
Okay, so I didn't say the Toffoli gate was a universal gate. I said it was a universal reversible gate.
Okay.
So if I want to reverse, you know what reverse means, right? If I want to
Yeah.
reverse, that is when I use the Toffoli gate. There is a classical equivalent of the Toffoli gate. So we needed to have a quantum version of it. That's why the Toffoli gate was invented by Tommaso. Any additional question?
Yes, please. I have a question.
All right.
About the while loop.
Okay.
In that line of code, you didn't create a
This one.
third qubit. No, in the while loop.
I'm at the while loop.
Yeah, in that code, you didn't create a third qubit for the while loop. So I want to ask.
Okay, so the preamble was to apply the Hadamard gate to two qubits and then measure them. So there was no need for me to create a third qubit because we're dealing with only two qubits. Please, do you get me?
Yeah, I get you now.
Yes, the condition was that we need only 2 qubits, and then we are testing for their states, whether they are in 1 1. So there was no need for an additional qubit in that regard. You know, qubits are very hard to come by, so you don't need to waste them. Is any additional question? If there are no more questions, then I'll hand over
Yeah,
to.
Esther,
Okay,
Esther is saying that kindly go over the first part of the repeat until
onto
success.
success. Okay, so repeat until success. You mean the code or the write-up?
From your question, is it kindly go over the first part of the repeat until success?
Okay, so I'm saying that um, I think I would like to start from here. So the repeat until success basically means that, let me show it this way so that you understand. Let's use this block sphere. What we are trying to do with the repeat until success is, let me clean this quick. Good. What we are trying to do with the repeat until success is, let's say I want to get to this particular state, right? But then anytime I apply my Hadamard gate, you know the Hadamard gate, it gives you 0 and 1. When you measure them, it's not always 0, you understand? Because it's in the plus state, I'm not always going to get 0. I'm going to get, it's a superposition. So there is a percentage of it being 0 and then a percentage of it being 1. Now the case is, if I want to get into this state, right? This state is between the minus and then the positive I. If I want to get into this state, anytime, because it is a superposition, anytime I measure this state, I'm not going to get specifically 0 and then specifically 1. Now the problem is, if you are not getting 0 for a definite amount of time and then 1 for a definite amount of time, so let's say it is splitting between 0 50% and then 1 50%. If it is not doing that, but their population, like the number of times it repeats, is random, it's random, it's random, it means that we need to repeat it as much as possible. In fact, if we perform it for 100 times and then we are getting, let's say, 60 40, 60 for it being 0 and then 40 for it being 1, and then we perform another measurement again and then it is skewing towards the 40, so we have let's say 60 being 1 instead and then the 0 being 40. You know, you cannot make a decision with an iteration like that. If for this particular moment I measure and then the thing is skewing towards 0, I measure again, it is skewing towards 1, I measure again, it is skewing towards 0. Like, in that regard, what you have to do is do it for multiple times. So in physics, what we normally do is, it's not advisable to perform just a single experiment and take your data. You perform the experiment for at least 3 times so that you sum them up and you find their mean, so that you know that at least this value that I'm getting is closer to the actual value. That is this. It is the same thing that we are trying to do with the repeat until success. We know that we are expecting, let's say, a 1, but the percentage or probability of the thing being 1 is so random that we cannot decide whether what we are getting is a definite 1 or it's not. So what do? We repeat it multiple times. We repeat it multiple times until we get a probability that we are sure of, that, okay, let's say this is finally, I've run it for like 1,000 times, I've run it for like 10,000 times, and it's giving me 70% probability of the state being 1. That is the repeat until success. That is what we are trying to do. I believe you get it. Now the rest is just code for us to visualize. So why I even brought in the block sphere is that what it means on the block sphere is anytime you measure, you will see that the value of the state will be moving a bit away or closer to the real thing, the real thing. So if I want to get it at least closer to the real thing, what do I do? It's the rotation that I need to do what? Correct it. It is the rotation that I need to correct it. That's why for the repeat until success, I made mention of this rotation gate. So I am supposed to be at the plus state, but the thing is between the plus state and then let's say the zero state, the plus state and the zero state. But I know that for sure the thing is supposed to be a plus. So what do? I perform it multiple times and then I'll get satisfied with time. I'll get satisfied that it will be okay. It's giving me, let's say, 70% of the thing being plus. Then I know the thing is plus, even though there's some element of zero state in there. That is why the rotation gate help us to rotate to the particular thing that we need. Are we okay? Okay. So if there are no more questions, I would like to end here. Thank you all for attending today's lecture. I think the rest of the conversation can happen in the WhatsApp group. So yes, we are supposed to submit the lab for today at a deadline of 11:59. Will applying a Z gate in a while loop ever break? As long as the condition for the while loop is met, it will go on and on and on and on. If you keep on applying the Z gate, what you are doing is you'll be seeing the same thing. So if I have 0 and apply the Z gate, I'm still going to get what? A 0. But then there is a phase in there. It's either plus or minus. There's going to be a phase shift in there. But you keep seeing the 0 at the same time, unless when you visualize it on a block sphere, because the block sphere doesn't give you phase. So if you keep on applying the Z, it will change. Just keep on changing the phase. All right, thank you. Please, I'll hand over to the moderator and then.
All right, thank you so much. That was a very wonderful presentation. I think I enjoyed the lecture. It was so understandable as well. So thank you so much, Ghana Quantum Guy. We appreciate such a wonderful presentation. And so let's give a thumbs up or, anything you want to say in the chat room just to support the lecture that just ended. So what is happening tomorrow? So we are crowning everything tomorrow, so soon. Everything is just ending. So tomorrow, 3rd November 2023, we are closing Qiskit 4 Fest Ghana, and we are ending with our challenge. So we are inviting all of you to participate in this challenge, which will happen tomorrow. So it's going to happen tomorrow, same time, 2 p.m. So we'll have the challenge, then we'll close the Qiskit 4 Fest for Ghana 2023. You may be asking, how is the challenge going to be like? So we all need to set up our IBM Quantum platform, because that is where everything is going to take place, in the IBM Quantum platform. So we are asking that you get a very good internet connection, get well connected for tomorrow's challenge. It will be a few exercises you will be given. We'll share that with you tomorrow, and you solve and we get the results. Then we are not going to do it like submit your assignment. Everything is going to happen tomorrow in our IBM Quantum platform. So if you still don't have your accounts working, this is the time. It is today to get it working. And If you have any other issues, please just get to know in the WhatsApp group. Let's get it fixed and let's participate. We will all get a certificate for this Qiskit 4 first. But to our nationals, the Ghanaians especially, we are saying don't end this session without participating in the Qiskit 4 first challenge. In the Qiskit 4 first challenge, we may have some few packages for you and all that. Maybe the first 3 for this challenge may receive some package from us if you are a Ghanaian, because you are here with us. It will be easy to get to you. So please, tomorrow, do not miss this session. Tell a friend to tell a friend. Come with your quantum codes, whatever. And let's end the session gracefully. So that is about the challenge. And we are submitting lab 3 assignments today as well. You can get the access to the lab in your GitHub. You download the folder, you find lab C there. You are submitting. The deadline for submission is today, 11:59 p.m. GMT. So kindly do not forget to do that. Then today's attendance link as well is in the chat room. I'm going to copy that again. So if you haven't filled the attendance for today, please kindly do so now. So I'm copying that again into the chat room. Okay. So you can kindly do so now. Fill the attendance sheets. And like we always do every day, we don't want to end this session without taking a snapshot. So if you don't mind, kindly put your videos on and let's take a snapshot.